All right, so I think we should be ready to start. Hi, everybody, and welcome to the 160th session of the Spectral Geometry in the Cloud seminar. Today we have Amir Vig from the University of Michigan, who will talk to us about Mach length, spectral invariance, and compactness of isospectral sets. As usual, if you have questions, either just unmute yourself during the talk or ask them in chat, and we will relay the questions. Amir, the floor is yours.
Thank you very much. Thank you for the invitation to speak here, and thank you to the organizers. I'm very happy to be in this wonderful seminar, which I've attended many times over the past 4 years now. Yes, so thank you to our organizers who we just saw on the screen. I wanted to just quickly say that the last time I was supposed to give a talk here, I was cycling just before in 2020 and took a tumble, which resulted in this awful surgery. So I was unable to do any kind of writing or typing for months afterwards. So I wore a helmet and was very careful for the last week or so to make sure I didn't end up in the same position. Okay, but so now we'll talk about Birkhoff billiards, and this is going to be the subject of the majority of the talk. Well, in fact, all of it. So let's let omega be a smooth domain in R2. So it has smooth and strictly convex boundary. This is what we call a Birkhoff billiard table. And we can assign to it an arc length parameterization of the boundary. So L here is going to be the length of the boundary, and S is going to be the arc length parameter. Strict convexity means that the curvature, just in the sense of multivariable calculus, is a strictly positive function. And the billiard map is defined as follows. If you take some point on the boundary and some angle with the tangent line at that point, then if you launch a billiard ball in the direction of that angle, starting at that base point, then it intersects the boundary at some other point with some other angle. So the billiard map sends arc length coordinate 1, comma, angle 1 to arc length coordinate 2, comma, angle 2. Okay. And the billiard map is defined by, you can iterate this by the law of equal angles. So angle of incidence equals angle of reflection, which is sometimes called Snell's law. Okay, so once we have the billiard map and its iterates, we can talk about periodic orbits. So these are ones that just repeat after some finite period. And they have a length spectrum, which is the collection of all lengths of those periodic orbits. Okay, in each periodic orbit, in the length spectrum, each periodic orbit, which has a length in the length spectrum, has a rotation number, and that's going to be some rational number, and it's going to be P over Q, where P is the number of times that your orbit winds around the boundary, and Q is the number of bounces. So if you have a triangle, an inscribed triangle, then the rotation number is 1 over 3. If you have a star, then this is a 2 over 5 orbit, and so on. So the Mach length spectrum basically just labels lengths in the length spectrum by their rotation numbers. Okay, so this is also called the maximal Mach length spectrum. And for every rational less than 1/2 and relatively prime, it assigns the maximum length of an orbit which has that rotation. So if P is 1 and Q is 3, the maximum Mach length spectrum of 1/3 is just the maximal length of a triangle periodic orbit. Okay. So the isospectral set containing omega is it's a set of all other all other domains for which the Mach length spectrum agrees with that of omega. So it's kind of like the Laplace spectrum. If you say it's a set of all other omegas which have the same Laplace spectrum, but here it's the same Mach length spectrum. And so the theorem is that for any Birkhoff billiard table, then the Mach length spectral set containing omega is compact in the C infinity topology on boundary curvatures. And furthermore, there exists a constant which is strictly positive, such that the boundary curvature is bounded below by that constant on the Mach length spectral set. Okay, so this basically tells us that Mach length isospectral sets cannot be very big; they're compact. And also, you cannot have degeneration away from convexity within an isospectral set. So the lower bound means that you cannot degenerate to having something flat. Okay. So hopefully the theorem is clear, but as Jean said, please don't hesitate to interrupt or ask questions if something's unclear. So the majority of the talk, or the rest of the talk, is going to be aimed at kind of saying a few words about how this theorem is proved and what are the ingredients which go into it, many of which are interesting in their own right. I see there's a comment in the chat. So Victor says, I would call strongly convex, leaving strictly convex for a weaker property, and Snell's law is the law of refraction, not reflection. This is true, but people still call it Snell's law. I don't know why. But yes, thank you for your comment. Okay, oops. So I wanted to just mention briefly the connection to the Laplace spectrum. So the above result on compactness also applies generically to the Laplace spectrum. So Laplace isospectral sets are also compact, and they have that lower bound on curvature. So this is a cartoon of the length spectrum of some domain. So you see that the lengths, they come in these little packets. Okay, so it's kind of like eigenvalue clusters, and they accumulate at the length of the boundary. So these correspond to these nearly glancing inscribed polygons with many, many edges. But for the Laplace spectrum, this result was already known by the works of Melrose, Osgood, Phillips, and Sarnak. But a lower bound on the curvature was not known. And so what's the connection between the Laplace spectrum and the length spectrum? It's due to the Poisson relation, which says that the wave trace, so that's, well, I should have written another trace. Trace of this operator is usually a distribution which is singular at the length spectrum. And in this case, the asymptotic distribution of lengths is Laplace spectrally determined. So if you have a distribution defined by the Laplacian, which is singular at these blue x's, right, then the distribution of these lengths also constitutes Laplace spectral invariant. Okay. The generic hypothesis is actually residual. It's a C-infinity residual property. It's primarily to avoid cancellations in the wave trace. And so that could happen when you have different orbits that create cancellations in the wave trace. So your wave trace could actually be smooth and a singularity is invisible. So this is the usual problem. And actually, together in a joint work with Ilya Koval earlier this year, we showed that this is really a necessary hypothesis. And this applies to all inverse spectral problems for the Laplacian. We show that for every natural number k, there's a large class of bounded, smooth, and strongly convex planar domains, such that the wave trace is locally ck near some point in the length spectrum. So this shows that we can almost make the Poisson relation a strict relation with a strict subset. Okay. All right. So that's the connection to the Laplace spectrum. So how are we going to prove any of these theorems? I won't say anything about the Poisson relation in this talk, but there is a preprint available. So we start with an arc length parameterization, as we did before, and we can define the cobalt bundle of the boundary to be the set of all cotangent vectors which have magnitude less than 1. So since this is in dimension 1, these are just numbers of absolute value less than 1. And if you recall in our picture on slide 1, phi is the angle made between a link and the tangent line to the boundary. Okay. So if we're looking at covectors which have magnitude less than 1, then we can set sigma to be cosine of phi. So this is some number between plus and minus 1. And you can think about it as being the tangential projection of this covector, which points inward from the boundary. So the billiard map, which if you recall sends S sigma to S prime sigma prime, is then a map on the cobalt bundle of the boundary. And it has a periodic generating function. So what do I mean by generating function? I mean that it depends on the position of the first point and the position of the second point. but not on the angles of reflection. And it has the property that if you differentiate in the first variable, you get the first angle. And if you differentiate in the second variable, well, you get minus the second angle. So this generating function actually contains all of the information that we need to describe the billiard dynamics. Okay, so here's a way of writing it kind of more geometrically. The billiard map sends S comma first derivative to S prime comma second derivative, or derivative in the second variable. Okay, so this is a generating function in the sense of symplectic geometry or dynamics. So some properties of the billiard map. The first one is that it's what we call exact symplectic. So what this means is that if you pull back the canonical one form, you get something which is the old canonical one form plus something exact. So if you take the exterior differential of this, you see that the billiard map is symplectic, right? Because d squared of h is 0. So the billiard map preserves a symplectic form. This is actually the reason why we choose cosine of phi instead of just phi between 0 and pi as a coordinate. It's because the symplectic form is best defined with sine of phi d phi ds, which is the same thing as sigma d sigma ds. F is a monotone twist map, which can be summed up in this condition on the mixed partials being positive. But geometrically, what it says is, well, if you recall that the first derivative is the angle, then if you fix 2 points on the boundary, and if you wind one of those points counterclockwise, then the angle at the first point must increase in order to have a link which connects those two. So it's just saying that, it's if you twist the angle, if you wind it counterclockwise, then the subsequent point of intersection with the boundary is also going to wind counterclockwise. So that's why we call it monotone, because it moves in one direction and it's twisting. Okay, so periodic orbits of the billiard map correspond to critical points of the so-called action functional. So if we think about the generating function as being an action, then if you fix 2 points, say S and S prime, and you look at 5 points in between them, then as a function of 5 variables, a critical point would of this function with fixed endpoints would correspond to a billiard orbit with 5 links. Okay, so this is what we call critical points in the sense of statistical mechanics. It's not a convergent sum or anything like that, but it's just a notation. So a theorem of Aubrey and Mather says that for every rotation number between 0 and 1/2, there exists minimal orbits of rotation number omega. So if h here, which is our action, is minus the length, then a minimal orbit, an action minimizing orbit, is the same thing as an orbit which has maximal length, subject to subject to some boundary constraints. Okay. So there always exists at least at least one minimal orbit having that rotation number. A theorem of Birkhoff says that if you have 2 integers which are relatively prime, so this corresponds to a rational rotation number, then there's always at least 2 orbits of that type. So Aubrey Mather says that there's always a minimal orbit of rotation of any rotation number, and Birkhoff says that if it's rational, there's at least 2. Okay. So it's good to know that periodic orbits exist since we're studying them. So a caustic it's a curve which leads to actually infinitely many, oftentimes periodic orbits. And what is it? So it's defined to be a curve inside the billiard table. So we can see here a curve like this one. I don't know if I have a laser pointer, but it's a curve such that if any link is tangent to this interior curve, then after an elastic reflection at the boundary, it remains tangent to the same curve. Okay, so in particular, periodic orbits circumscribe, periodic orbits which are degenerate, they can circumscribe these caustics. And this is a picture of an ellipse, and the ellipse is foliated by confocal ellipses and confocal hyperbolas. And it turns out that those are all caustics. So here in blue, we see a bunch of orbits which are tangent to confocal ellipses. And in purple, we see a bunch of orbits which are tangent to confocal hyperbolas. Yeah, and they make this very beautiful picture. So this image is courtesy of Alfonso Sorrentino. Here's two other pictures. Again, the one on the left is due to Alfonso, and this is perhaps easier to see. So for a circular billiard table, concentric circles are caustics. If you ever have a link which is tangent to a concentric circle, then after reflection at the boundary, it remains tangent to that same concentric circle. Okay. So on the cobalt bundle of the boundary, which is our phase space, these caustics, they project to invariant curves. So though I tried to draw those here. So the billiard map will take in one point, maps it to another point, maps it to another point, maps it to another point, and caustics are just these C infinity invariant curves for the billiard map. Right, and we can forget about zeta. I'll talk about zeta in a couple slides. S star plus here is this is the glancing region. So it's the unit sphere bundle, but in 1D. So it's just plus and minus 1. So more on caustics. It's true that as a consequence of the KM theorem, there's a bunch of caustics. So Lazutkin showed that there exists a Cantor set of positive measure such that for every rotation number in that Cantor set, the billiard table has an invariant curve of that rotation number. So it's really a lot of caustics. Oftentimes, these are irrational caustics, so they don't correspond to periodic orbits. And as usual from the proof of the KM theorem, these rotation numbers satisfy some Diophantine property. The Diophantine condition is what gives us the structure of a Cantor set. It is possible that you can have rational caustics, like for the ellipse. So to every caustic, we can associate a parameter called the Lazutkin parameter, and we're going to call it Q. So I'll explain this picture in a second. But geometrically, you can think about having a string, and if you cinch that string taut around a caustic, so this caustic here is this dotted line, then the length of that string doesn't depend well, it depends on the caustic, but it doesn't depend on where you wind it around. So in other words, the boundary of the domain is an evolute of this caustic from this string construction. The length of the string minus the length of the caustic, if you just add and subtract those numbers, you can see is the sum of these two red links minus the arc length of this curve in blue, which connects the 2 points of tangency. If you have 2 points of tangency on a caustic, you add up the length of the links connecting them with the boundary, and you subtract the arc length of the minimal arc between them, and that's an invariant of the caustic. It's called the Lazutkin parameter. So Mather's beta function is going to be one of the main objects of study. It says the following. So if you take any minimal orbit, which has rotation number omega, and you average the generating function over that orbit, then the limit is going to be some number. It turns out that it exists. And we call that Mather's beta function. Okay. And so if you remember, this generating function was the length. So in particular, if we have a rational rotation number, so omega is p over q, then here 2n is the number of bounces. That's the number of links. Excuse me. So if you just divide by the number of bounces, this is the same thing as Mather's beta function. So Mark length spectrum and Mather's beta function are essentially the same. Mather's beta function has just been renormalized. Okay. Any questions about this? This is really a lot. And of course, there's a whole lot of stuff that goes into proving all these things are well-defined, but I figured I would just tabulate it kind of axiomatically. So some properties of the beta function. So these are due to Aubrey and Mather. And again, I'm just going to tabulate them. So the first property, which is I find extremely surprising and kind of amazing, is that the beta function is strictly convex, and in particular, it's continuous. That is not at all obvious to me. It's symmetric about 1/2. That's a little bit more obvious. And it's 3 times differentiable at the boundary. The derivative of the beta function at 0, which, 0 rotation number basically corresponds to infinitely many bounces winding around once, which is essentially just one gliding orbit. So the derivative of it equals minus the length of the boundary. it turns out that this function is also differentiable at every irrational between 0 and 1/2. And it's differentiable at a rational if and only if there exists a caustic of that rotation number. So when we say a caustic of rotation number p over q, what we mean is that every orbit tangent to that caustic is periodic and has rotation number p over q. If gamma is a caustic of rotation number omega, then the derivative of beta at that rotation number is in fact the length of the caustic. So you can see actually that omega equals 0 is a special case of this. If you think about the boundary as being a caustic, then you differentiate it at 0, you get the length of the boundary, but this is true even in the interior. And so this is kind of a very deep theorem. It turns out that there's a formal asymptotic expansion of the beta function as the rotation number goes to 0. So of course, the beta function might not be smooth. All we know is that it's continuous and differentiable at some points. But since we have this Cantor set of rotation numbers corresponding to caustics, then we know that our beta function is actually differentiable on a Cantor set. And that is enough to define a formal Taylor expansion. Okay, and these Taylor coefficients are Mark length spectral invariants. So these beta I these are what we're going to use to show Mark length spectral compactness or isospectral compactness, because on any isospectral set, these beta i's are constant by definition. So if we can describe the beta i's in terms of some geometric information and show that, we're going to describe it in terms of curvature, if we can bound curvature and all of its derivatives in terms of these beta I, then we'll be good to go. So for every strictly convex function, there's what we call a convex conjugate. It's also called the Legendre-Fenchel transform and is defined as follows. For some number I in what we call the action interval, if we take the supremum over all omega of omega I minus beta of omega, we get some number. It turns out that this supremum is actually a maximum. And so we can find a critical point by, if you differentiate this thing in omega, you get I minus beta prime of omega. So if you plug in, if that's 0, then you can just plug in I equals beta prime, and that gives you the convex conjugate. Okay. And so it's just a fact about general convex conjugates that the derivatives of these things are inverses of each other, functional inverses, not multiplicative inverses. So alpha prime of beta prime is the identity, and beta prime of alpha prime is also the identity. And it's a theorem. It's fun. I mean, it's a multivariable calculus proof, but one can show that if you have a caustic of Lazutkin parameter q, then it turns out that Mather's alpha function, when evaluated at the length of that caustic, is in fact the same thing as the Lazutkin parameter. It's really a fun proof. It would take maybe 2 slides or something, but I think it's believable. And there's a theorem which is from what I could see, is due originally to Marvisi and Melrose in the 1980s. Later put in the language of Lazutkin parameters by Seeberg and others. So there exists an asymptotic expansion of the length of a caustic in terms of the Lazutkin parameters. So as the Lazutkin parameter goes to 0, our caustic is approaching the boundary. The length of the string is becoming closer and closer to the length of the boundary. So I0 here is essentially going to be the length of the boundary. And this power 2/3 is kind of mysterious. If you know this Airy calculus, for example, for FIOs and Airy FIOs and stuff, this 2/3 is kind of ubiquitous in the literature about glancing orbits. Okay, so it turns out that these invariants IK, are algebraically equivalent to the beta i's, and they're actually a little bit easier to work with, so we're going to use those. But you can go back and forth between the IKs and the beta i's. So I just want to show you the first couple invariants. just to get a flavor of what they look like. So let's denote by kappa sub I, the ith derivative of boundary curvature in arc length coordinates. So Marvisi and Melrose, they found the first two invariants. The first one is what we call the Luzukin perimeter, not perimeter, but perimeter. And it's the integral of curvature to the 2/3. The second invariant is this kind of bizarre looking integral. So it's an integral of the curvature to the 4/3 plus first derivative squared over kappa to the 8/3. Okay. So one thing actually to note about integral invariance of curvature is that the integrand is not unique. You can always integrate by parts, right? And then you get, it's a closed curve, so you have no boundary terms, and you'll always get the same invariance, much in the same way as you do for heat invariance. Okay. So Alfonso Sorrentino found the next two invariants, and as you can see, their complexity grows exponentially. So the third invariant is it's some polynomial in the curvature Z with coefficients in 1 over the curvature. Okay. And the fourth one is an even longer polynomial. But so these are the first two formulas that I saw that made me want to prove compactness in the beginning. And what I noticed is the following. I1 has no derivatives of curvature. I2 has one derivative of curvature, and it appears with a square. Okay. I3 has at most two derivatives of curvature, and it also appears with a square. I3 has, well, here's two. Let's see. There should be three somewhere. Where is it? Where's the third derivative? Kappa 1 squared, kappa 1 squared, kappa 3, kappa 1. Here. Thanks. So there's three derivatives of curvature squared. Moreover, every term in this integrand, if you add up the total number of derivatives, here it's 4. It's 2 plus 2. Here it's again 4. It's 1 plus 1 plus 2. Here it's 6. It's 3 plus 3. Here it's 4. Here it's 2 plus 2 plus 2. But it's always less than or equals to 6. So there's some kind of beautiful algebraic structure which is hidden in these coefficients. And what I wanted to show is that you can essentially focus on one term, which is highest derivative squared. If you can do that and ignore all the lower order terms, right, then if you can show inductively that they're constant, because, again, these IKs are mark length spectral invariants, right, then you can bound all of the Sobolev norms of your curvature in terms of mark length spectral invariants. And that's what's going to lead to compactness. Okay. And as you can see, there's almost no hope for computing these invariants with all of the coefficients exactly. But I think we found a pretty good algorithm for how to do it. So let me just show, it's a fun little computation. In general, I don't like the idea of proving things on slides, but this one is just so cute, I couldn't resist. Okay, so let's look at I2. Let me just remind you what I2 is. So it's 1 over 5, this one. It's just two terms in the integrand. It's, some constant, curvature to the 4/3 plus another constant, and then first derivative squared over something else. Okay. So if we get rid of the first term, which is positive, we can bound from below the second invariant by, this is just the second term. Okay. We can rewrite this as kappa to the minus 2/3 log derivative squared. Okay, so why is that true? Log derivative is kappa prime over kappa. Square that, you get kappa prime squared over kappa squared. Kappa squared is kappa to the 6/3. Okay, so then we add in an extra 2/3 out here. And then there's this amazing estimate. So everybody knows Holder's inequality, but there's also what we call a reverse Holder inequality. So this is where P, instead of being greater than 1, is less than 1. And instead of giving a bound from above, you get a bound from below. So we apply that here with P equals 1/2. That gets rid of this square. And Q then is minus 1. Right? So you have to have 1 over P plus 1 over Q equals 1. So Q has to be minus 1. And if you notice this kappa to the 2/3, that's just the first integral invariant. That's I1. The second one, well, this is the L1 norm of the log derivative, and it's just fundamental theorem of calculus that, you know, the C0 norm of a function is bounded from above by the L1 norm of its derivative. So if we can, so we get this log over here, and here's the amazing thing. If log of curvature is bounded, then curvature is bounded above and below. How amazing is that? I don't know. I mean, I had really so much fun playing with these invariants. So this is kind of how I felt about myself after doing this invariant. It's not much, but it's honest work. Okay, the other ones are more difficult. So can we show that this structure that we saw in the first four invariants persists for higher order invariants? And the answer is yes. So this is a theorem that I showed last year. It says that for each k, these ik integral invariants have the following form. They're integrals of polynomials in the curvature Z, and they have differential degree 2k minus 2. That just means that there's at most 2k minus 2 derivatives. You add up all the derivatives, you get at most 2k minus 2. And the highest order derivative appears quadratically, just like we saw in the first four. So here's the highest order derivative squared. Okay. Yes, there's some silly coefficient, but you can actually check that this is the same one as it appeared in the I1 through I4. You have some linear term, and then you have a remainder. Okay. And the linear term and the remainder have a lower differential degree, and they don't depend on, and they don't depend on the highest order derivative. So the idea is that we want to inductively show that the L2 norms of these curvatures are bounded in terms of the L2 norms of the previous ones, which were in turn bounded by the IKs, these Mark-Length spectral invariants. All right, so I know this is a bit messy, but basically we can think about this theorem as just, you know, showing that the above patterns that we observed are in fact real. So let me just say briefly how the structure theorem on the previous slide implies compactness. We can use the third invariant, which if you remember, it is some longer polynomial in the curvature Z. We can use that to bound the first derivative of curvature. And once we have that, then we can inductively bound all of the L2 norms of derivatives of curvature. And so this uses one of these, it's an interpolated Sobolev inequality, which is really an amazing one. This one kind of encapsulates all of the other standard Sobolev inequalities and allows for fractional powers. And also there's this interpolated exponents. Once we have L2 bounds on the norms of the curvature, on the derivatives of curvature, you can use the usual Sobolev embedding to bound the CM norms of curvature. And once those things are all bounded in terms of Mark-Length spectral invariance, our Zila-Ascoli theorem implies compactness. So that's kind of how that argument goes. You know, it's a mess of formulae, but it's true. And so what I want to show you for the rest of the talk is kind of how do we arrive at that structure theorem. It's very geometric actually in nature. Are there any questions so far? All right, let me know if I'm going too fast. Okay. So here's a sketch of the proof, or really just I don't know, cinematic overview of the proof. So we use Melrose's equivalence of glancing hypersurfaces, and this gives us the existence of what's called an interpolating Hamiltonian. So what is an interpolating Hamiltonian? It's a C infinity function on the cobalt bundle, which is our phase space. And why is it called interpolating Hamiltonian? Well, the billiard map is then given by the time one map of the Hamiltonian flow of this function, okay? So we don't actually use the function, we use it to the power 3/2, which is again this kind of ubiquitous but enigmatic power of 3 appearing. But this is nice because now, I mean, you know, we use the word interpolating because the time one map of a flow is kind of interpolating, you know, as you flow around for all t. We also use what we call action angle coordinates, but our billiard map is not completely integrable. It's almost integrable, so we have to use action angle coordinates in the setting of the KM theorem. And these are due to Kovachev and Popov, and based on earlier work by Pochel. So they're symplectic coordinates theta comma I, such that the billiard map is conjugate to a rigid rotation in those coordinates. So this is a rigid rotation. You keep the same I, that's your action variable, and your theta just goes to theta plus a rotation. Okay, and so this holds at least on a Cantor set of positive measure containing the boundary. That's the same Cantor set that we've seen a couple times now. Okay. And it turns out that we can take the action variable to be the length of a caustic, and its symplectic dual is going to be our angle variable theta. And in that case, Mather's alpha function, which is the convex conjugate of the beta function, is an interpolating Hamiltonian. That's kind of a magical fact. Essentially, it boils down to the fact that alpha prime of I is omega. So, theta I plus alpha I generates the billiard map as a generating function in the symplectic geometry sense. And using the work of Kovachev and Popov, comparing it with this alpha function, we see that actually this is a good choice of interpolating Hamiltonian. And this one's nice because we now have a very geometric interpretation of the generating function. So how do we get these invariants IK? They're going to be Taylor coefficients of what we call an action integral. Okay, so the level sets of zeta are approximate caustics. And let me remind you that our billiard map is the time one map of this Hamiltonian flow, and the Hamiltonian is always constant along flow lines. So if the billiard map is given by this time one map up to infinite order near glancing, then level sets of the interpolating Hamiltonian are approximate caustics. Okay, they're approximate invariant curves. So we can choose a one form dz, which is dual to the Hamiltonian vector field in the sense that dz of the Hamiltonian vector field is 1. And we can note that zeta dz plus ds is a primitive of the symplectic form. Okay, why is that true? Well, d zeta wedge dz, that's just omega, which is the same thing as d sigma wedge ds, and d squared s is just 0. Okay. So we can interpret the integral eta over a closed orbit as being the abbreviated action. If we extend zeta in a natural way so that it kind of fixes a cohomology class, then our primitive of the symplectic form is cohomologous to the canonical one form, which is sigma ds, right? So in particular, if you integrate the canonical one form over a caustic, you just get the length of that caustic. So the action and the length are the same thing for this kind of flow. And we can always pull out zeta in an integral like this because, well, zeta is constant. So let's just introduce kind of a further abbreviated action, which is just the integral of the one form dz over these orbits. Okay. So this thing has some Taylor expansion, and these IKs are precisely the IKs that appeared in the length of a caustic expansion a couple slides ago. So T is going to be Lazutkin parameter to the power 2/3. All right. So it follows, okay, so this is what we just said, that our action is T times I of T plus the length of the boundary. If you integrate ds, right, over a caustic, you just get the length of the boundary. And if we recall that our interpolating Hamiltonian was Mather's alpha function, which is the same thing as the Lazutkin parameter, we get that expansion, right? There's a weird power of 3/2 in front, but it's just a constant. Okay. And again, just to reiterate, these IK are what we're going to use to show isospectral compactness. These IKs are integrals of curvature polynomials. All right. So this expansion is, again, it holds as Q goes to 0, which means that your orbits are more and more glancing. They, they correspond to whispering gallery modes in the Laplace spectral sense. Okay. So how do we compute these integral invariants? We can expand our interpolating Hamiltonian near the glancing region. Okay, so if we let lambda be 1 minus cosine of phi, as phi goes to 0, right, this means that your angle of incidence, or your angle at which the billiards emanate, is approximately tangent to the boundary. So 1 minus that cosine of that angle goes to 0. And here we're just writing a formal Taylor expansion of our interpolating Hamiltonian. Okay. So if we just write out that action integral, but in coordinates, it's the integral of 1 over the derivative of this Hamiltonian. Okay, and the lambda here, the dual variable, is defined implicitly in terms of t, which is the level set. So these are those curves on the invariant curves on the cylinder, which we saw a few slides ago. So we can expand this thing in lambda, and then recall that lambda depends on t, so we differentiate in t, and we get some horrible expression. So we get a horrible expression, and we're going to keep track of it. I don't want to write it because it's a nightmare, but we're going to keep track of it. So let's just assume that we start at a base point, which is where the arc length parameter is 0. We can always rotate and translate so that this is the case. And in fact, we can put this point at the origin if we have the domain tangent to the x-axis. So let S prime be very close to S. So you're looking at a very short link, which connects S and S prime. Okay. Then using our interpolating Hamiltonian, we can write S prime as the image of the time one map of this Hamiltonian flow, and we can expand this thing. Okay, so we can expand it so it's called a Lie series, and what I mean here is that you just expand in terms of this vector field. So pretending this is exponential of a number, we can we would take higher and higher powers of this vector field. Although that's a combinatorial problem, which is pretty hard in general, actually. If you have a Hamiltonian vector field, so you have d zeta di dd theta minus d zeta d theta ddi, not in action angle coordinates. If you take that differential operator to a high power, what are the coefficients? An easier version of this is if you have a function of one variable, f of x. F of x ddx is a first order differential operator. What are the coefficients of f of x ddx to the power n? It's that one, it turns out there's an easy answer to. And in the 1D case, you can reduce the Hamiltonian vector field to that case. But in higher dimensions, there's no explicit formulae. It's in terms of rooted trees, or at least that's the best I could find. Yeah. So we can use this to compute S prime, the subsequent point of intersection with the boundary, algebraically. Okay. And these AM, they come from taking high powers of this Hamiltonian vector field. And so they contain polynomials in the jet of the interpolating Hamiltonian. I mean, if you have f of x ddx and you expand it to the power n, of course, the coefficients of that differential operator are going to be polynomials in the derivatives of f, right? And it's the same thing here, except for you have two variables instead of one. Okay, so we expand that, compute it, and save it for later. And now we want to do the same thing, but geometrically. So recall that lambda is 1 minus cosine. Okay, so we can write this in some silly, we can write this in just, I don't know, plug it into Mathematica. You get some combinatorial coefficients. You just Taylor expand lambda. Okay, and if you draw a triangle, right, you can see the tangent of the angle of reflection is just rise over run. So if you're centered at the origin, your rise is x2, that's the vertical coordinate, divided by x1, that's the horizontal coordinate. And if you start differentiating this thing at the origin, right, well, since you're constraining yourself to lie on the boundary of our curve, this thing has a Taylor expansion, and the coefficients are defined, they're in terms of curvature. So this is kind of where all the curvature stuff comes in. So you have tangent of the angle can be expanded in terms of the subsequent point of reflection with coefficients in the curvature jet. So these CP are differential operators. But we also know that phi of S prime has an expansion in terms of the, whoops, this is actually not phi prime, sorry. I wanted to write S prime. Yeah, I want to write S prime has an expansion in terms of this lambda from above. So that was that was this lambda. S prime has an algebraic expansion, and here's a geometric expansion. And now we equate the two. Whoops. When we equate the two, everything is defined implicitly. So it's not at all clear how can we solve for the coefficients of the interpolating Hamiltonian in terms of those of the curvature jet. And if we do so, it's going to have to be inductively, because at each step you're going to have Taylor coefficients of the interpolating Hamiltonian of all orders less than some fixed one in terms of the curvature jet. So you're going to need to do it, you're going to need to solve for each Taylor coefficient of the interpolating Hamiltonian inductively. Those are zeta I of S. So I know this is a lot. So once we do that inductive procedure, we can keep track of highest order terms in curvature, highest order derivatives of curvature. And when we compare them, we can invert a very nonlinear map, which sends polynomials in the curvature jet to rational functions in the Taylor coefficients of an interpolating Hamiltonian. This is that inversion process. You substitute in those coefficients of the interpolating Hamiltonian into the action integral, and you integrate by parts to lower the number of derivatives as much as possible. And what do I mean by that? This is, again, let's just do a 1D case. If you have a function f of x, and you have some polynomial in f, f prime, f double prime, f triple prime, right, then if you integrate that, you can always integrate by parts. You can move over derivatives from f triple prime to f prime, for example, and then you get f double prime. So is there an algorithm by which you can integrate by parts and obtain the minimal number of derivatives in an integrand? And the answer is yes. And that's what we do. That's how we get these integral invariants. Okay. When we do that, as if you remember, the first 4 invariants were these terrible formulas, and they had all kinds of crazy coefficients. So if you solve in general for the highest order terms, you have to use tools from analytic number theory. You're solving something inductively, you put coefficients in generating functions, you solve some differential equations. And at the end, at least I was completely surprised that there was some connection with the Riemann zeta function. So the Riemann zeta function evaluated the even integers, those appear in the coefficients of the highest order derivatives. And in fact, you can, I went back and checked this against I1 through I4, and it's really the case, which is kind of it's a complete miracle to me. Okay, so those are the main ingredients in the proof, which obviously I don't have enough time, or presumably nobody else wants to see that proof in its entirety. But I do want to mention some future work. So all of this is in the direction of Birkhoff's conjecture. So I haven't told you what that is, but Birkhoff's conjecture asserts that only ellipses have completely integrable billiard dynamics. Okay. Completely integrable means that there's a foliation by caustics. Okay, so if you remember many, many slides ago, I had that picture of an ellipse and I had another picture of a disk. So disks are foliated by concentric circles, and ellipses are foliated by confocal ellipses or confocal hyperbolas. Okay, so Birkhoff's conjecture is that only holds for ellipses. Okay, now if you remember that stuff about Mather's beta function, we said that the beta function was differentiable at a rational number if and only if there exists a caustic of that rotation number. So you can rephrase Birkhoff's conjecture as saying only ellipses have smooth beta functions. Everywhere else, your beta function is not smooth, it's singular. Okay. So since we're studying those invariants, right, then the end goal is to use them in Birkhoff's conjecture, or at least in approaching it. And a natural next question is to study what are the Taylor coefficients of beta away from the boundary, or correspondingly, what are the invariants IK? We found an expansion near 0, which is the nearly glancing orbits, but our Cantor set of rotation numbers, we can define, at least in the sense of Borel, a Taylor expansion at any accumulation point really in that Cantor set. And those coefficients might be actually more useful. I think the same algorithm should work. Right? And just one note is that the IKs cannot be used to show rigidity. And why not? Because suppose you have a disk where the curvature is constant. If you add 2 bumps to the disk and you translate those bumps around, your integral invariants are exactly the same. This is a standard construction from heat invariants for the Laplace spectrum. So in other words, you can just translate those bumps around. You keep the same Mark-length spectral invariants. You keep the same integrals, right? But of course, the domains are not isometric, right? They have they're very different. So you can't use these local invariants of curvature to study rigidity. However, away from the boundary, those integral invariants are possibly useful. In fact, a long time, like 40 or 50 years ago, somebody tried to prove Birkhoff's conjecture by studying caustics of caustics. So for an ellipse, a confocal ellipse is a caustic, and confocal ellipses of that confocal ellipse are also caustics. So anyways, that was approached a long time ago, and I think there's more to be said for that story. And I just wanted to mention that if you can use rigidity to show local uniqueness, it would follow that Mark-length isospectral sets are finite. And that would also apply to Laplace isospectral sets, at least in this generic setting. And by the way, the generic setting includes analytic domains. So it's not that restrictive of a condition. And I should also mention that in the boundaryless case, where you have manifolds of negative curvature, people also study the Mark-length spectrum, and there's a result of Colin Guillermo and Thibault Lefebvre that shows that in that setting, you actually have local uniqueness. So if they could get this kind of compactness, then again, you would get finiteness of isospectral sets. There's also something called symplectic billiards. So these were introduced in the last couple of years by Albers and Tabashnikov. They're again integrable twist maps, or almost integrable twist maps. They're symplectic. They preserve the area form, or rather the symplectic form is a generating function as opposed to the length function. So you could ask whether or not you can prove compactness in that setting. I think so. And yeah, more generally, I would really love to know if you could generalize these results to geodesic flows on manifolds without boundary. And again, that would have really some tremendous implications in showing that Mark-length isospectral sets are finite. But that seems to be very hard, and there's a completely different toolbox. And for example, in the setting of negative curvature, you don't have Aubrey-Mather theory, you don't have integrable twist maps or any of this kind of stuff. But nonetheless, it would be very interesting. So anyways, I think this is a good place to stop. So thank you very much for your attention and for inviting me to this wonderful seminar.
Thank you very much, Amir, for the wonderful talk. So Victor is asking in the chat what one can say about 3D domains, etc.
That's a great question. Is it known that 3D domains have caustics? If you have a cavity, like even an ellipsoid, I agree that confocal ellipsoids should have some special property, but I guess you would study the surface area of those confocal caustics. I know there's some work by people doing lower dimension invariant tori. So I think you would have invariant curves in higher dimensions, but probably not invariant surfaces. Yeah, thank you. That's a nice question.
I have another question. It's Colin de Verdier.
Oh, hey, thank you.
Do you know if there is some relation between your invariants and the heat trace invariant, which are also, because in this case, maybe you could prove that if you are isospectral, then you have the same. I don't know, but I'm sorry. Yes.
They certainly look like the heat invariants as integrals of polynomials in the curvature jet.
Yeah.
But what I think is nice about these is that they're completely dynamical. So Melrose 40 or 50 years ago used the heat invariants to show isospectral compactness for Laplace or isospectral things. So if from the heat invariants you could figure out these invariants, then my result would be very boring. But I don't think so, actually.
Okay.
So you can go from the length spectrum to the Laplace spectrum by this kind of Melrose stuff, but you can't go the other way in terms of.
Another approach, maybe for relating with the Laplace spectrum, is what did Lazutkin, building some approximate eigenvalues from the caustics, because the Lazutkin invariant is also an action integral on the invariant torus. So you have two action integrals, which are the length of the caustics and the Lazutkin parameter. And from that, you can build the Bohr-Sommerfeld conditions and try to get something from the approximate eigenvalues, which, as far as I remember, is a positive density part of the spectrum. What was proved by Lazutkin. I don't remember exactly, but it's related to the fact that the counter set is really more and more dense near the boundary. And the measure is positive. Maybe, but it's only for approximate values, and only for a part of the spectrum, but should be related to more or less to your invariant. I don't know, but
yeah, I mean, I think Lazutkin show he found quasi-modes, right, which are like whispering gallery modes, and they accumulate to the boundary. But you could do the same thing at an invariant curve away from the boundary, as long as it's an accumulation point for this Cantor set of tori. So I don't know, maybe you could find even you know, more eigenvalues or quasi eigenvalues.
Okay, thank you.
Well, thank you. That's a nice question.
Maybe a silly question, but if you were to consider a surface without a boundary, would there be an equivalent of these whispering gallery modes? Where would it be?
Let me think about that for a second. You have a surface without boundary. What would be? Well, for example, if you take an ellipsoid, or a sphere, rather. I mean, yeah, so a sphere or ellipsoid has completely integrable geodesic flow. And if you perturbed it a little bit, then the KM theorem would give you that there's a Cantor set of invariant tori. So these would be higher dimensional tori. And I guess you could look at accumulation points of those tori as corresponding to whispering gallery modes. So they're higher dimensional now, but I mean, you just take a sphere and then you put some bumps on the sphere. So you perturb the geodesic flow just a little bit. And originally, your whole phase space, the cotangent bundle or cobalt bundle of the sphere is foliated by invariant tori, which is the 2D family of 2D tori. And if you perturb it, a positive measure of those tori persist. And that's sort of the same, at least that's sort of analogous to what happens near the boundary for billiards. So I suppose you could look at the accumulation points of those tori as being whispering gallery modes or something. I know Yves Collin-Verdier has a paper on quasi-modes on Riemannian manifolds. And I think, correct me if I'm wrong, but I think this is creating quasimodes associated to elliptic geodesics, which are closed. And you could do something similar on an invariant surface.
Okay, but maybe the question is, if you have a strictly convex domain in R3, do you have still some caustics close to the boundary? I don't know if it's known. I mean, the extension of Lazutkin to higher dimensional domain, it's not.
Actually, okay, so I believe the following is true. If you are in higher dimensions, if you have a convex body and there's one invariant surface, like a convex but invariant surface, then you're an ellipsoid. Just a single one. Not even a foliation. So this is like Birkhoff's conjecture, but like on steroids, and it's true.
So does anyone else want to ask a question to Amir?
Maybe I have a so you mentioned a few times these generosity properties in terms of the Laplace isospectral case to avoid certain cancellations. Is it easy to describe in a way what kind of things you need to what is this meager set you need to avoid?
Yeah, so let me go back to that. Yeah, it's actually not better. So Marivisi and Melrose call this the non-coincidence condition. And is let's see. Yeah. Okay, thank you, Alexandre. So I had this little cartoon here where you have these clusters in the length spectrum. So actually, one thing that's kind of interesting is that if you have a completely integrable billiard table, these clusters are just singletons. So you just have, and you should think about those singletons as being eigenvalues, Laplace eigenvalues on the sphere. Okay. If you perturb the sphere, there's these things called Weinstein band, you have these clusters, and there's Weinstein band invariants, which study what's the distribution of eigenvalues within those clusters. But these clusters look actually very similar. So they accumulate at the boundary, and our marked length spectral invariants, they capture at what rate do these clusters accumulate there. So you have these, say, just 1 over q orbits. So 1 over q, as q gets large, these are polygons with q sides. They get closer and closer and closer to, they piecewise approximate the boundary, and their lengths accumulate there. The non-coincidence condition is that there's no orbit of winding number bigger than 2, which has lengths approaching the boundary. So, if your domain is analytic, for example, there's only finitely many lengths, below the perimeter with winding number bigger than 2. But in general, I think there are domains. Jacopo di Simone has some construction which I think can carry over. So you could construct domains where this condition fails. But yeah, essentially the condition is that at least in some neighborhood near the boundary, the only points in the length spectrum are those coming from polygons with winding number equals 1.
So do we have any further questions? In any case, we're not going to close the session straight away. So I think we can certainly thank Amir again for a great talk. We'll meet again next week with a talk by Julie Rollett, who is going to tell us about the spectral invariance of integrable polygons. So yeah, in the meantime, please be free to chat with Amir again a bit more if you have any further questions.
Thank you so much for the invitation to speak here. Thank you.